So now the last example in 6.4 is again a more applied problem, lots of steps to it, but we're going to break it down. So we have a Boeing 757-200ER airliner, carries 200 passengers and has doors with a height of 72 inches. Heights of men are normally distributed with a mean of 69.0 inches and a standard deviation of 2.8 inches. So if a male passenger is randomly selected, find the probability that he can fit through the doorway without bending. So, okay, well, so we have, let's draw our picture here. So we had 69 in the middle, and it really doesn't give you much as far as the value of x in here of what they're analyzing. But if you go back to the beginning information, it says, okay, the door has a height of 72 inches. So now let's think about this. If we can have a passenger go through the doorway without bending, hopefully they're what compared to the doorway, the door height? Hopefully they're shorter, right? If they're shorter than 72 inches, then they don't have to duck. But if they're taller than 72, then they're going to go tong and hit their head on the door if they tried not to bend. So they have to be shorter than 72 inches. So that is what we want to look for. So shorter means less. So we're going to be on this side. So that should be what they're looking for. And now what's n? N in this case, if it's a male passenger, only one. So a male passenger should tell us that n is equal to 1. Okay, so now we have a pretty good idea of what's going on. So we have our x equal to 72. So let's convert it. So we had 72 minus 69 all over 2.8. So now, let's see what that gives us. So 72 minus 69 equals, divided by 2.8 equals 1.071 blah blah blah. Okay, so 1.07 if we round it to 2 decimal places. All right, so then we have to go to our table and look up the probability. So let's get our tables. Now we're on the positive side, positive 1.07. So 1.0 and 7 is 8577. 0.8577. And are we done? Yeah, there's not really anything else that we got to do. We have it shaded to the left, so we can see that it's over half the bell is shaded, so that corresponds to that. So we should be good. If half of the 200 passengers are men, find the probability that the mean height of the 100 men is less than 72 inches. So now it's kind of the same thing, but now we have an n. So be careful. They're trying to trick you by throwing in the 200 first, but it's only half. So actually n is right here. So n equals 100. So we still got our bell, still got 69 in the middle, and we still got 72, and we want less, so we want the left side again. So now, though, the only difference is we've got to use our modified z-square formula. So we got 72 minus 69 all over 2.8 over the square root of 100. So remember, if you do the bottom first, so really we're dividing it by 10, which moves the decimal point over one spot. So that's going to equal 0.28. So now, if we do the number crunching, so 72 minus 69 is 3. 3 divided by 0.28 equals 10.714, yeah, blah, blah. All right, so again, we want to, this is a z-score, so we want to round it to 2 places. So 10.714 0.71. And so now, if we go to our table and look at the probability, 10.71. Well, we got a problem. The table only goes up to 3.5. So 3.5 and up is 0.9999. So we don't even have to get fancy. So almost 100% chance that the average height will be less than 72 inches for those 100 people. So individually, we got an 86% chance that the one person, the one male, is less than 72 inches, but almost 100% chance that the average of 100 men would be less than 72 inches. So that's interesting. Part C says, when considering the comfort and safety of passengers, which result is more relevant, the probability for Part A or Part B? Why? Now, this is a little different than the previous problem with the water taxi. The water taxi, we wanted the average to be less than 180 pounds because otherwise it would capsize the water taxi. But if we're considering the comfort and safety of passengers, do we care more about the individual or do we care about the average? Now this one, like I said, is different. We actually want to look at the individual and make sure the individuals are happy, because you might have those anomalies where you have a really tall person and you want to make sure that they're comfortable, long-legged people. So in this case, the average situation is irrelevant. So we would want to look at Part A. So ensuring individual safety and comfort, or comfort and safety, should be more relevant. So again, we're pretty confident that most individual men will fit, but we still want to look at the individual case. And now Part D says, when considering the comfort and safety of passengers, why are women ignored in this case? Yeah, we don't even talk about women in this. But what do we know, statistically speaking, about the heights of men and women? More often, women are shorter than men. That's just a statistical fact. So that's why if the men can fit through the door, then there's pretty much a guarantee that the women should be able to fit through the door. So statistically speaking, women are shorter than men. So if men fit, then women should fit also. Again, not a great politically correct answer, I know, but that's essentially what they're getting. They're looking at it from a statistical perspective, not a politically correct perspective. So just keep that in mind. All right, so that wraps up this section. Now, again, just to summarize, the last page of the notes just has this summary, which is hopefully would be useful to you. So again, the problems need to be asking for probabilities or percentages. So if we have that happening and it involves an individual, so n is equal to 1, then we use the same processes as we did from 6.2. So we have our x values that we start with, we change them into z-scores, and then we find the probabilities from the table. So again, we still have to use that table every problem that's normally distributed. But when we have sample scenarios, so if n is greater than 1, or in this case, if n is greater than 30, then the original population can have any distribution we want. And in that case, we can apply the central limit theorem to the problem. So we find our x values, we change them to z-scores using our modified z-score formula, because n is not 1, and then we go to our table and find the probability. So use those z-scores and find the probability. And then the last case is when we have a smaller sample, so it's less than 30, but the original distribution the original population is normally distributed. So if that is the case, so both of these have to be in effect. If it's smaller and it's normal, then we can still use the central limit theorem. So we find our x values again, we convert them into z-scores using our modified z-score formula, and then we use those z-scores to find the probability from the table. So, alrighty, that wraps it up. Stay tuned for more videos to come.